Hi, and welcome back to part 2 of chapter 2. We're going to be getting into comparative studies now. So a comparative study design studies the relationship between an explanatory variable and a response variable. Explanatory variable is the treatment or exposure that explains or predicts changes in the response variable. The response variable is the outcome or response being investigated, right? So response variable sounds just like what it is. It's the response of what you're looking at. You know, if you jump up and down, your heart rate is going to rise. Response variable will be heart rate, right? The explanatory variable will be jumping, a very simple thing, right? Is the treatment or exposure being explained? That's the explanatory variable here. In comparative studies, which may be experimental or non-experimental, you can have explanatory or response variable. In the experimental design, the investigator assigns the subjects to groups according to the explanatory variable, right? So this is the key part here. You have an experimental design, the investigator is going to assign groups according to the explanatory variable, i.e. they're going to be exposed or unexposed. Whereas in non-experimental designs, the investigator doesn't assign subjects into groups. Individuals are classified as either they have been exposed or non-exposed to the explanatory variable. So to kind of show you what this looks like here, you have an experimental design, which when you have a random assignment, you're going to be randomly selected, right, to either go to group 1 or group 2, and then there's going to be a treatment process, and then you're going to measure the outcomes, right? Whereas in non-experimental designs, you have classified individuals, and then group 1 is going to be the individuals who are exposed, and group 2 are going to be ones who are not exposed, and you're going to compare the outcomes. To show you what this looks like in a little bit more detail here, here's an example of an experimental design. So here we have a Women's Health Initiative study randomly assigned about half its subjects to a group that received a hormone replacement therapy, right? So here HRT, hormone replacement therapy, is the explanatory variable, and then we're measuring to see what the response is after getting the HRT. So subjects were followed for 5 years to assess various health outcomes, including heart attacks, strokes, the occurrence of breast cancer, and so on. So here you have an experimental design, and the subjects were assigned, right, to get the treatment, or potentially what they're probably going to do in experimental design is also have a controlling area where they're going to get a placebo group 2. So, but they, in either case, the placebo group or experimental group are being assigned, right? They're randomly assigned into those groups, and then they're measuring for heart attacks, strokes, and occurrence of breast cancer, and so on. In a non-experimental design, so here we have the NURS's health study, which classifies individuals according to whether they received HRT, right? So in this one, they're not experimenting on HRT, they're merely classifying whether the individuals received HRT. The subjects were followed for 5 years to assess the occurrence of various health outcomes. Might seem similar, but it's really based upon the classification of the explanatory variable. So here we have comparison of experimental and non-experimental designs. So in both the experimental and non-experimental design, the study relationship between HRT, explanatory variable, was for various health outcomes. The various health outcomes are the response variables, right? We want to see how HRT was there, and both are different. One was an experimental design, one was non-experimental design. In the experimental design, the investigators controlled who was and who was not exposed, right? If you were an experimental, you may have been in this potentially maybe the second group, and could have been a placebo group, so you never actually got the drug, and they wanted to see how getting HRT, affected these health outcomes. Where in the non-experimental area, both groups are based upon whether or not the individual did receive the hormone therapy. They didn't sign up to receive it, they may have gotten it through other various methods or reasonings, and they wanted to see whether or not the individuals who were exposed to it over 5 years, how the response variable occurred. So here we're going to focus on select experimental designs, concepts, and techniques. So experimental designs provides a paradigm for non-experimental design. So here we have a setup. So we have our study design at the top, and we're either going to have an experimental or observational study design. Key thing when we do our case studies, a lot of times I'm going to ask you, is this an experimental design or an observational design? I'm going to ask you, what kind of study design is it? Don't say it is a simple random sample, or I don't know, there's been some other interesting ones. I want to know, is this an experimental or an observational design? How are these groups separated? That's what we're really doing in statistics, right? We're comparing most of the time we're comparing a lot of groups to each other and seeing what the difference between them is. But is the design an experimental one, where the researcher assigns exposure, or is it an observational, which the researcher observes the exposure? And then as we go down through, we're going to get into these different types of more specific study designs. These will come up more towards the end of the semester when we really get into it. But during the case studies, you will see a lot of these different ones. You'll see cohorts and case controls, cross-sectional. You'll see meta-analysis type study designs. And really, if it's not experimental, right? If you don't see some sort of experiment going on where they're testing something and having a control group, and compared to an experimental group, it's going to be observational, right? Because they're just observing what's going on. Those are the two main types here that we're going to be looking at. So there's some jargon we should go over. A subject in our lingo is an individual participating in the experiment. A factor is an explanatory variable being studied. Experiments may address the effects of multiple factors. And a treatment is a specific set of factors. Just some definitions for you to know as you're reading on throughout the course. So we have three important experimentation principles. First is controlled comparison. Second will be randomized controls. And lastly will be blinding. So controlled comparison, so we have a controlled trial here. The term controlled in this context means that there is a non-exposed control group. We have to measure it against what would happen if the drug isn't there, right? Having a control group is essential because the effects of the treatment can be judged only in relation to what would happen in its absence. Think about if you're taking aspirin. If you have a group of people who have a headache and you give half those people aspirin and the other half nothing, the response variable will be probably the people who took the aspirin. Their headache will go away quicker than the people who did not take it, right? At least that's kind of like a simple way to look at it, right? We have a control group of people who are absent from taking it. Now the people in this control group will probably take an aspirin. It'll probably be a sugar pill, or what we call a placebo effect pill, and it's just it's not real. It's not there. Cannot judge effects of a treatment without a control group, as many factors contribute to a response. Conditions change on their own over time. This placebo effect or other passive interventions affects the operation. Having a control group helps with all of these. If you don't have a control group, like I said, all these other factors can contribute to what's going on. But if we can control to the best we can, then we can measure how well like an aspirin works compared to not taking an aspirin. Next up we have randomization. Once again, random is random, and it's probably one of the most important things to always take into consideration when there is any kind of data or statistics going on. It's the second principle of experimentation. It refers to the use of chance mechanics to assign treatments. Randomization balances lurking variables among treatment groups, mitigates their potential confounding effects, right? Even though we like to think that sometimes maybe we pick completely random, a lot of times we've actually, studies have shown that we are biased. In some way or another, what you think is actually random is not random unless it comes from a random digit table or a random number generator. You cannot just randomly go on a list and just randomly pick students. Somewhere subconsciously it's truly not random, and it can be exposed as not being random. So we want to make sure it's there, that we have randomization. So another randomization example, we can consider this study. We have an explanatory variable, which is nicotine or a placebo patch. We have 60 subjects in each group. We want to see if they stop smoking, as their response. So we have them. We have this random group, and we want to put 30 of these smokers in each, and then one group is going to receive the nicotine patch, and the other group is going to receive a placebo patch. And then we want to compare and see if the nicotine patch actually helped reduce smoking. So if we have these 60 individuals, we want to randomly put them in different groups, right? So we have 32 tuplets right here between 0, 1, and 60. So remember, we're looking at our largest value and how many significant figures it is. So we have 60, so it's 2 significant figures. So we want to make sure our first one has 2 significant figures too. So it'd be 0, 1 to 60. And we're looking for 2 tuplets, right? So tuplet, remember, being an order array, an order list of anything. So we're looking for 2 of them there between 0, 1, and 60. We're going to use our table A, and we can arbitrarily select a different starting point each time we want to. So for this one, we're going to use, let's say, line 19. If you go to line 19, in your table A, or random digits table, right? You can, once again, you can find that on page 539. Go to line 19, you'll see these values, the first 5 sets each here. And we're going every 2. So the first one we're going to look at is 0, 4. Well, 0, 4 falls between 1 and 60, so that's going to be in it. 24 is our next 2, that's going to be in it, and 73 is not, so that's not included. 87 is not, 98 is not, 73 is not, 28 is, and then we would keep going all the way through. One thing to keep in mind, though, because we're looking for 30 individuals, right, between 0 and 60 to put into these 2 groups, we look for 30 individuals, we're going to go through the first line. Like, we're going to finish line 19. The more individuals you're looking for these different groups, you're going to keep going. Once you finish a line, you just keep going. So then after you finish line 19, you go to line 20. And after you finish line 20, you go to 21. You just keep going all the way down the list until you find all the individuals you need. So here we have we identify randomly 2 tuplets. Here we go. We kind of went over this in the last slide. You want to ignore tuplets that are greater than 60, and you want to ignore duplicates, right? So say we had 24 pop up again. Well, 24 can't be in the group twice because there's only one individual who's number 24. Therefore, 24 we would just cross off, and we would just keep going like we normally do and keep moving along the line. 24, an individual, remember these aren't just necessarily numbers, they're individuals, and they can't be in a group twice. So you keep going until you find your 30 individuals in this group. And then once you have your first 30 individuals in the group, that would be your first group. And then naturally, since you have 60 and the other 30 are going in the other group, you only need to find the first 30. Everyone who wasn't selected will automatically go into that second group. Now, if you had multiple groups, say you had groups, if you had 60 individuals and you wanted 6 groups because you were measuring different things, or you wanted just to measure it against 6 different groups, like you can do that. But remember, you would take your first 10 would be your first group, next 10 would go into the second group, third group, so on and so forth, and you keep going, and you cross off any duplicates or anything that's greater than the total number of individuals you have in your sample. The remaining groups are sent to control. We just talked about that. So, and then the last thing we have here is blinding. So blinding is the third principle of experimentation. Blinding refers to measurement of response of the response made without knowledge of the treatment type. So we want to prevent unnecessary differential misclassifications of the response. We want to reduce bias of any kind. So there's different levels of blinding. We have single blinding, double, and triple. Single blinding is where the subjects, individual participants who are in the treatment, do not know what they are getting. So if you were an experimental design and there was single blinding, you don't know whether or not you're getting an actual nicotine patch or a placebo patch. You don't know. But you are the only person who doesn't know in a single blinding. The nurses, the doctors, the statisticians, anybody else in the research does know where you are in that thing. And that is a single level blinding. It's not the strongest. As we keep moving up, it gets stronger. So double level blinding are the subjects and investigators are blind. So if you were doing this nicotine patch, the nurses and the participants or people administering the nicotine patch don't know what area you're on. And this is one of the better ones because they don't know where you are in the study. They can't guide you through questions. It's just not good. It's better for more people not to know. The last level of blinding, triple level blinding, the study subjects, the investigators, and the statisticians are kept in the dark. Basically, only one person, probably the PI, the principal investigator, only knows where people are, and that's it, and that's the strongest type of blinding. Last but not least, we have ethics. So we have informed consent, beneficence, equipoise, which is the balance of risk, benefits and risk judgment, and then independent IRB oversight, IRB institutional review board. All these are in place. You have to get an IRB in order to conduct studies to make sure that everything that's going on is ethically sound and correct, and nothing can hurt the individuals. There's plenty of examples throughout history where ethics comes into play with study designs. We won't get into all those, but know that ethics does play a part in research, and it has to be accounted for. All right, that is the end of Chapter 2. I will see you all next week.